So hello everyone. So today we have a great pleasure to have Dr. Yubo Su visiting us today. So Yubo got his bachelor degree from Caltech, and then he went to Cornell and worked with Dong Lai on dynamics of astrophysical systems and got his PhD. So now he is the prestigious Lyman Spitzer Jr. postdoc fellow at Princeton. So Yubo has a wide range of research interests ranging from planetary systems to neutron stars and black holes. And he is an expert on dynamics. Today he will tell us about tidal locking in exoplanetary systems, where the planets will have permanent day side and permanent night side. So thank you.
All right, hey Ruby, thanks Kunti for the kind introduction. Before I start, I also it's great being back at Georgia Tech. I actually grew up in Georgia. I'm up in the Johns Creek area. I'm actually back home for a friend's wedding, and so I did come to campus occasionally for like various random little high school events here and there. So it's kind of cool to be back. Some 15 years later. 15 years after the fact. So it's very cool. Glad to be here. I'm going to be talking a little bit about spin dynamics, tidal locking of exoplanets, basically. I was told that there's a pretty wide range of background and expertise here. So can I just get a quick sense of astronomy and physics majors in the audience? Or I don't know, majors or like specialties-ish. Biology? I'm missing some very big fraction. Is that like the interdisciplinary
Chemistry.
Chemistry, of course. Okay. Chemistry.
Earth and Atmos, planetary.
Okay, there we go. Okay, that's probably the one that I was missing. Yeah, with the most important planet. That makes sense.
Engineering.
Oh, okay. So we've very. Oh, sorry. I probably could have checked on Zoom as well. Okay. Cool. Great to have all of you guys here. I think that it's my first time trying to give a talk to, I think, an audience with like such a diverse background. I've tried to. I'm kind of a theorist who wants to understand why certain things occur, and so I wanted to take this chance to kind of convince you guys that some of our ideas for avoiding tidal locking, while they at first glance may seem a little bit like extreme, are not so surprising and actually can be understood in quite basic and simple ways. That's going to be the goal here. I think it was a very satisfying process for me to figure that out. But if it's not clear for you guys or anything, please stop me, ask any questions. I think the seminar is very much so for you guys. So let's just keep it. Please just feel free to interrupt anytime. Okay, so the story today is going to start with, it's a story about the obliquities of planets. The obliquity of a planet is the misalignment angle between the planet's spin axis and the plane in which it orbits its host star. So for example, Earth's 23-degree obliquity is why we have these very hot summers and our very relatively chillier winters, right? I think it should be surprising, if you think about it a little bit, that Earth has this 20-degree obliquity because, well, we think that planets form out of a disk, something like illustrated here. And if you just take a cloud of the disk gas and you collapse it into a planet, the planet should be spinning in roughly the same direction as the disk was initially oriented, right? So you should kind of expect a lot of your planets to have zero obliquity. As I mentioned, we're already 0 for 1 kind of with the Earth. What about the other planets in the solar system? All of the obliquities are actually not 0, except for Mercury, almost all. So Venus is famously on its upside down. And you can see there's a couple of other interesting exceptions, right? Even Saturn, something that's so big, right? You have to find some way to get it to form or later evolve to an obliquity of like 30 degrees. Saturn's a very big planet. That should be kind of surprising. Uranus and Neptune are also, Uranus is spinning on its side. This story of 0 obliquity at formation doesn't seem to work as well as necessarily you would expect. And that should be a little bit surprising. But this is only 8 planets. Maybe we can know something about exoplanets, right? We've discovered something like 5,000 planets beyond our solar system to date. What do we know about their spin orientations? That would be a great question to answer if we could. It turns out that it's a little bit hard. There we go. Okay, great. The obliquities of exoplanets are generally quite hard to measure. A few years ago, the first constraints started to be able to be put on what we call planetary mass objects. These are guys that are like 10 times, maybe even like tens of times the mass of Jupiter. They're orbiting their host stars at like 50 AU, so like 50 times the distance that the Earth is from our sun. There have been about 4 of these, 3.5. This last paper is currently on its way out. There have been 3 to 4-ish objects for which that has been constrained. And tentatively, it looks like a lot of these objects are also rotating on their sides. That's also interesting. Other than that very direct measurement mechanism, you can also make some new deductions based on the some recent observations with the James Webb Space Telescope. You can maybe like look at the spectra of secondary eclipse when the planet passes behind its host star. You can look at the high resolution spectroscopy a little bit, and you can kind of constrain, what elements there are in the planet's atmosphere, what the temperature is, and you can kind of put some constraints on how hot that planet is and whether you would expect it to, whether that might tell you something about the spin state of the planet. You can also actually directly map out it's kind of crazy. You can kind of map out the temperature on the planet as a function of its latitude and longitude for some very, very idealized cases. But this is like a planet that's like really, really far away. We can kind of identify where its hottest point is. And it's a very exquisite measurement, and something that's only become possible in recent years with the James Webb Space Telescope. And there are also various other more indirect ways that you can also start to try to understand what the obliquities of planets are. But broadly, it's a hard measurement to make. We don't really have that much more information concretely than we do within our solar system today. There's probably one more dynamical constraint that I should have put on there. Okay, so what should we have expected for exoplanet obliquities? Why is it? Would they be any different than what we see in the solar system? Over here, I'm showing kind of the exoplanets that we've detected to date. This is the radius of the planet, and this is the orbital period, so kind of a proxy for the distance to the host star. I've labeled for your convenience the 4 close-in planets in the solar system, and you can see that most of the planets that we've detected are bigger, and they're closer into their host stars. These are the ones that are a lot easier to detect through the techniques that we have today. And yeah, so they're close in. They're close into their host stars. They're big. This means that the host star will cause the planet will raise a tidal bulge on the planet that's much stronger than anything that we typically see in the solar system. So just like how on the Earth, the oceans bulge a little bit due to the influence of the Earth, Sun, and the Moon, you should expect the same process to be happening for these planets here. And that process should drive these planets towards becoming tidally locked. And in fact, that is actually very efficient for exoplanet systems. Over here in the red dots, I've kind of color-coded the planets that should become rapidly tidally locked within about 10 million years. 10 million years, blink of an eye for these systems. They're typically a few billions, they're billions, like hundreds of millions to billions of years old. So you should expect these planets to be confidently in this tidally locked state, where they just have a permanent day side and night side. They go around their host stars, and because they spin at the same rate as they orbit, there's just one side of the planet that constantly faces this host star. You should broadly expect that these red dots should all be tidally locked. In the solar system, you can see that only Mercury is kind of in that regime. If you go to like Venus, Earth, Mars, and of course the further out planets, they should not be very much affected by tidal dissipation. This is kind of the story that you would put together, and that's why you would expect most exoplanets to be tidally locked. However, there are ways to avoid this, and the one that I want to talk about today is called a secular spin orbit resonance. This is something that's been studied for many decades now, with or without tidal dissipation, in the solar system context quite a few times. Gives rise to something called the Cassini states. And the interesting one that's kind of neat is that, well, there's one boring Cassini state where the planet's obliquity is 0 as it orbits the star. But there's also another one where these Cassini states give you ways for the planet to rotate on its side, very, very close into the host star, even though there's some amount of tidal dissipation going on. So it would be great if these can bring us away from tidal locking, because it'll kind of change your atmospheric retrievals that everybody's looking at right now. It gives you some answers to various dynamics questions, and also I think for some of the people here, it'll affect your climate on the planet, it'll affect your habitability of the planet. So it'll be kind of interesting to look at how prevalent this sort of a phenomenon can be. Yes, question?
Yeah, you said on the previous slide that tidally locked planets spin at the same rate at which they orbit, so that they're always facing their star or their sun. And I was wondering, is there some kind of equilibrium mechanism that causes that spin to be at the same rate as the orbit?
Yeah, that's a good question. So I think that the idea is basically just that if my star raises a bolt on the planet, the planet itself is trying to rotate at one rate, but this fluid on top is always pointed towards its host star. So if those two frequencies are different, then there's some extra dissipation. The lowest energy state is where the planet rotates at the same rate so that the bulge always points towards the star. And it is always it always points towards the star, and there's no dissipation at this like interface with the planet. So there is some dissipation mechanism that you would expect. That's the process that's occurring on this like 10 megayear time scale. Good question. Any other questions? Okay. So you guys probably do have questions about how the heck you get onto this perpendicular thing. Hopefully I'll have explained that by the end of the talk. Great, okay. So let me just briefly hop back. So we've talked a little bit about tides, we've talked about spin orbit resonance, and I also at the beginning teased like, there are 8 obliquities in the solar system. Let's label them with like kind of what's going on with each. Indeed, Mercury is experiencing pretty strong tidal dissipation. It's like well to the left of this red line here. That's why its obliquity is 0 degrees. Venus does something weird because of some atmospheric tides stuff, some different mechanism that allows it to be spinning retrograde. Earth and Mars both also have some interesting spin orbit dynamics that let it be tilted. Well, actually, Earth, Mars, Jupiter, Saturn, all are doing like non-trivial spin orbit things that are proposed to give them their non-zero obliquities. And then the obliquities of Uranus and Neptune are attributed to something different. They probably got hit by a giant impact, other planet sometime in the distant past that caused their spins to tilt. So within the context of all of these solar system obliquities, we've kind of, over the course of the past, 50, 100 years, put together stories for all of them. And maybe between the processes that I've introduced so far, we can already kind of understand what's been going on in the solar system. Okay. I think, I don't know if anybody was around for Gunja's talk like maybe 6 months ago. If you are, I'm sorry, some of this might be repeated, but I'm glad that you're back. If you haven't, I think this is mostly an annual seminar class, right? So maybe there's not too much overlap. Yeah, so let me tell you a little bit more about planetary spin dynamics. The talk is going to go through a couple of phases, so I just wanted to make sure that at all times we kind of have the big picture direction of the talk in mind. The first thing that I want to talk a little bit about is what are these secular spin orbit resonances, and why do you expect like a 90-degree obliquity during this resonant phase? So when we talk about spin orbit resonances, I think the easiest one to visualize is actually just a very basic one-to-one spin orbit resonance. And this is one that I think all of us can probably understand. So you take a planet, and if it's slightly football shaped, it's a little bit elongated along one axis. The one-to-one spin orbit resonance is the lowest energy state where the long axis of the planet always points towards a star as it goes around. So the purple arrow and the green arrow are always pointing at each other. And this is your one-to-one spin orbit resonance. We call it a resonance because there's 2 frequencies in here that are equal, right? The frequency at which the planet orbits its host star, and the frequency at which the planet spins about its own axis. So it's technically a resonance in the sense that 2 frequencies are crossing, but unlike, maybe if you remember in your physics classes where like you take a simple harmonic oscillator, you drive it at resonance and something like blows up, right? It's not quite necessarily a violent resonance like that, but because it does still correspond to an equality of 2 frequencies in the system, we still talk about it as a resonance like this. But in all of these resonances that I'll be talking about, we do want to look for 2 frequencies that become equal. Okay, so that's kind of what I mean when I'm talking about resonance. What did I mean when I said that we were talking about a secular spin orbit resonance? This is something that's pretty common when we think about how systems of planets, systems of exoplanets evolve. We like to think about it in the so-called secular approximation. In this approximation, you take the planets and you average over their orbits so that you can effectively think of the planets as rings of mass that are pulling and tugging on each other. This means that if you're trying to do any like numerical simulations or anything, instead of trying to resolve the planet going around the host star really quickly, you now can take much bigger time steps, and your planets are a lot easier to understand and evolve So that's the motivation for kind of doing this orbit averaging approach. It also simplifies things at the pen and paper level quite a bit as well. So that's what I mean by secular. I guess the motivation for doing this secular evolution, of course, is that planets, they orbit their stars on like a year, tens of days or something. And I want to understand how planetary systems evolve over billions of years, right? It's not going to be very feasible to just toss this into a computer and evolve it forwards in time. Okay, so that's why I called it a secular spin orbit resonance. But as I showed you earlier, for any resonance, we need two frequencies that will have to become equal, right? For the purposes of this, for most of this talk, I'm just going to pretend that we're in a two-planet system. So like you have an inner blue planet and an outer black planet. The theory kind of works out if you extend it to multi-planet systems as well, and I'll touch on that a little bit towards the end. What are the two frequencies that are equal? The first frequency is something called orbital precession, which happens kind of on thousands to millions of year timescales. And actually, it's very easy to understand why this happens. You can kind of see it by eye. The outer planet here is this black. I'm looking in the plane of the orbits, so the outer planet is some sort of a black line. The inner planet is kind of a blue line. The black line exerts a gravitational force on the inner planet that kind of tries to align it with the plane. And if you do your like R cross F, that results in a torque that comes out of the page. And you can kind of follow this exercise through a couple of times as the system evolves. What you will end up finding is that due to this torque over time, the blue arrow will kind of trace out a cone shape about that black arrow. The torque again points outward, so you come out of the page, etc. This is what I mean by orbital precession. So I mean secular orbital precession, or you can just think of it as two vectors. One traces a cone kind of around the other. The second precession effect is spin precession, and it's not that much more complicated. The idea is that I have a planet, and my planet is spinning, so it becomes a little bit rotationally flattened at its equator. If I take a ball of water or gas, whatever, and I spin it, it should be a little bit fatter at the equator due to just rotational flattening, right? You solve for it, or it becomes rotationally flattened, and in that case, the star also exerts a gravitational force on the planet. Same R cross F exercise. What you find is that the planets will also tend to precess about the orbit normal. So these are the two precession effects. Both of these, you'll notice I've labeled up here, kind of occur on thousands to millions of year timescales. It obviously depends on the exact planets that you're looking at, but you can see that it's quite conceivable that the two of them are going to be equal. And what happens when they're equal? What happens when we're in this resonance where the two are equal? I tried to make a couple of videos to show you guys what this looks like. Again, reminder, the secular spin orbit resonance has to look like equality of this secular orbit precession rate, which is, again, the blue vector traces out this cone about the black. The precession rate occurs at some g minus g times cosine I. The negative sign is just an old convention from like I guess it must be like sometime in the 20th century. And I is the angle between these two orbits. It's some small number. You can think of cosine I as just 1. So that's one precession frequency, minus g cosine I. The second thing that happens is this spin precession that I was telling you about, where the red vector is going to try to trace out a cone, but it's tracing out a cone about this moving blue vector now. That occurs with some rate alpha times cosine of theta, where theta is the obliquity. And now you can kind of see it, right? If I ever want to set these two frequencies equal, that's going to place a constraint on the obliquity. And that's kind of the knob that we get to let the obliquity enter the picture for this spin orbit resonance. In this resonance state, what happens is that the precession frequencies become equal. And you can see that kind of the S and the L vector precess in a way such that they are always, it's a little bit hard to see from here, but they're always kind of in a plane with one another. And that gives you a way to make sure that S and L are misaligned even when the inner orbits are circular, which is kind of neat. So you get large obliquities even with circular orbits. Okay, when do you expect this to occur? Well, the condition that we want to satisfy in order for this resonance to be possible is this. I've just set the two frequencies to be equal, right? Of course, if this g cosine I is greater than alpha, there's no solution for cosine theta. Cosine theta can never be greater than 1. So the only way that we can get a resonance is if G cosine I is less than alpha. And in that case, the obliquity that you pick out is this ratio over here. And this is the state where I was telling you guys about Cassini state 2 earlier, this very tilted state on its side. And in particular, what you should notice is that when G is really small compared to alpha, that there are ways to then the cosine of theta goes to 0 and you get really, really large obliquities. And this is kind of the picture that you have where the planet is tilted on its side. I've hidden a lot of stuff away in G and alpha. I'm happy to introduce those in a little bit more detail if you guys are interested, if you want to apply to your own planetary system of toys. But the point being that if you can find a system where G is much less than alpha, then you can get very large obliquity. Then it's possible for your planets to be in these very high obliquity states. Yeah, so we've done this study before. We've looked around a little bit, and you might expect something of order 10 to 100-ish, maybe, systems of the 5,000 that we've discovered to be in this frequency regime and have like an appreciable rate of being captured into here. So there's a decent target list. Okay, great. I guess I do want to make a quick mention of this, which is just that again, inside the spin orbit resonance, you have to be in this high obliquity state. When you have tidal dissipation, the planet's spin tends to be driven towards this value, which has been like understood in the literature for a long time. And what you should recognize is that cosine theta is really small. So that corresponds to a very, very slow spinning planet. So these secular spin orbit resonances also result in very subsynchronous rotation of the planet. So instead of having your tidally locked state, you have a planet that's spinning on its side and is spinning really, really slowly compared to what tidal locking should give you. Great, okay. So that is kind of what happens with the secular spin orbit resonance story. So it can drive the obliquity to large values, and it drives the spin to a subsynchronous value. And this is also stable even if you have this tidal dissipation process acting on the planet. Okay. Brief pause. Does anybody have any questions so far? Okay, great. Second topic is, I hopefully I've convinced you that it's not very far-fetched that this high obliquity state exists. You can really understand it as just, forces and torques and these like right-hand rules, stuff that you've really been learned in like your intro physics classes, right? So it's not that mysterious of a phenomenon, but now the question then becomes, how did the planets even get to these large obliquities in the first place? If you're telling me that my planet forms with nearly zero obliquity, how do I actually reach this high obliquity state? For this, there are kind of two primary ideas. The first idea I think is one that I've worked on, and I think is is a little bit simpler to understand, which is just that, Earth-ish and Neptune-ish mass planets, it's generally thought that when they formed, they probably experienced a phase of giant impacts very early during its formation, which kicks the spin axis randomly. This is kind of like what we think happened with Uranus, right? So the planets are made, like the initial spin of the planet might be pointing downwards after all that, it might be pointing on a side, it might be pointing outwards in some crazy way. We won't be able to observationally observe this because the obliquity then tidally damps, again, over this like millions or tens of millions of year timescales. So the obliquity, so this red arrow corresponding to the spin of the planet will eventually all damp back to zero anyway, pretty quickly. Naively, it should damp back. So we probably wouldn't expect to see the large initial obliquity necessarily. But remember that earlier we said that there's this resonance condition where as long as my G cosine alpha is less than 1, there's some small range of obliquities where I'm satisfying this resonance condition, right? So the idea should be that if my planet's spin is damping, then it crosses through this purple region where I pass through this resonance, and then where I pass through this resonance. So you should kind of expect that there are generic ways for planets that are forming to be captured into this resonance just as a consequence of their natural evolution. So as you tidally damp, you see that the red vector, as it's going towards the blue arrow, passes through the purple region. And then the question is, what happens when it hits that region, right? You're not resonant, not resonant, not resonant. Suddenly you hit the resonance, what happens? Do you stay there, or do you kind of continue to move on all the way to this to the standard like tidally locked zero obliquity state? Turns out that that outcome is actually probabilistic. There's a sensitive dependence on the initial conditions in here, so you get some probabilistic capture into this high obliquity state. So if I'm in a system with satisfying like g over alpha less than 1 roughly, the picture should then just roughly become like, if I start out with an obliquity that is less than 90 degrees, then it never passes through the blue region, right? If I damp from here, it goes all the way to the blue, never pass through, so it should immediately become tidally locked, no questions asked. However, for retrograde systems, there's some probability of capture, and anything that's not 0 and less than 100 is 50, so if half of my systems that are retrograde get captured into this high obliquity Cassini state 2, what you might expect is that something like a quarter of systems that satisfy this condition, this G over alpha condition, are located in this high obliquity Cassini state. That's kind of just the guesswork. This is kind of just to give you guys an idea of what sorts of numbers you might be expecting here. I can show you the actual plot that pops out when you do this very carefully. For this, again, I've been focusing on 2-planet systems, but let's imagine, for concreteness, I'm going to plug in some numbers for all the frequencies that I gave you. The system that I'm considering is a planet that is maybe like 10 times the mass of the Earth and 2 times the radius of the Earth. So it's what we would call a super Earth or a sub-Neptune, somewhere around there. And it's surrounded by just a standard Jupiter planet. It's a Jupiter-like planet at 5 AU, which is Jupiter's orbital distance. And it's orbiting a star that's very much like our sun. In this system, there's some key parameter that you have to evaluate called eta sync. It has to do with the ratio, this G over alpha ratio that I told you about earlier. And it turns out to be about 0.3. If I look over here on this plot, 0.3, what does that correspond to? The bottom panel here tells you the probability of being trapped into this high obliquity Cassini state. It's about 30%. And then up here, I'm showing the actual obliquities of the 2 Cassini states. And so you can see that about a third of the time, my obliquity should be about 60%. And 2/3 of the time, the obliquity should be maybe like some small, like 10%, 10 degrees, sorry, 60 degrees or so. Down here, I'm maybe like something like 10 or 10 degrees or so. So the prediction should be then that if we ever are able to measure these obliquities for these super Earths and cold Jupiters, maybe like about a third of them are in this high obliquity state, where the obliquities are something like 70 degrees or so. And it turns out that for these planets, they're spinning at maybe like half synchronous or so. So yeah, so the picture that I built for you earlier, where maybe like 25% or so of planets are spinning on their sides, it's not so far off from the truth. It kind of depends a little bit on your parameters here. And in the paper, we go into excruciating. Oh, I forgot to put. This is the paper that I was. This is one of my papers from 2 years ago. We kind of go into excruciating detail about exactly what happens in this process, and you can kind of work things out and really understand what is happening analytically. How do you get captured into the resonance, etc. Happy to talk more if anybody is interested in understanding a little bit more about that. Okay, so the second mechanism by which this can happen is a little bit nicer in some ways and a little bit more uncertain in some others. This is a slightly older idea by Cheryl Holland and Greg Laughlin in 2019. So their idea is basically just that if you start out with a system that satisfies the no resonance condition, but then planets form inside their protoplanetary disks, so they interact with the gas around them and they will migrate. They will tend to drift inwards because they feel a headwind as they go around their host stars. So they undergo orbital migration, they move inwards. This causes alpha to decrease, and so you can transition from the no resonance case into the resonance case. And it turns out that in this case, you actually get guaranteed capture into this high obliquity state. Over here, I pulled a plot from their paper, and what you can kind of see is that the blue line is the obliquity of the inner of their 2-planet system. You can see that it starts out around 0, and eventually it happily gets captured into this high obliquity state of around 50 degrees or so. Down here are the precession periods, and you can the frequencies remain equal in that case, and that's showing you that you are indeed in that resonance. So the pro of this mechanism, it turns out, is that the capture into the resonance is guaranteed, and there's already evidence in the exoplanet systems that we've seen for orbital migration. It's a little bit, the con is that I think that if your planet is inside the disk already, you can imagine that the disk does a lot of things other than just orbital migration, and it's still something that's being worked out whether any of that affects this orbital capture or not. So there's a couple more uncertainties compared to the previous mechanism that I was telling you about. Okay, did I have one more on this? No, okay, great. So, but the upshot of that piece is just that, these high obliquity resonances do exist. They give you subsynchronous spins. And there are two mechanisms that you can kind of look at two mechanisms identified so far about how you get captured into these resonances. And they have pros and cons, but there are two different ways. They both give modest rates of being captured into these high obliquity states. It's something that you might want to be considering, right? If you're looking at, I think that this is enough to kind of conclude that, exoplanets, there should be some of them that are stuck in these high obliquity, weirdly spinning states. Okay, any other questions? Okay, great. I think that that's like the primary piece of the story. I think that in and of itself is now kind of a complete story, right? You can now take that and go and make predictions. But before we do that, I think that there are a couple of complications that I'd kind of like to talk about, because I think that this is kind of an understanding of, you build out your nice story, you want to go out there and write your important papers, and then an observer comes and asks you, okay, so what should I look at? And then suddenly you have to start thinking about complications that you may not necessarily have thought about in the past. So the first complication is that, as I said, we've so far only been considering 2-planet systems. But most exoplanet systems that we found are not 2-planet systems. The solar system is an 8-planet system. 2 planets is probably not very realistic. For just a single 2 planets, what you get is this one orbital precession. There's one vector that's tracing out a little cone shape. However, and in that case, the misalignment angle between the 2 vectors is constant. The mutual inclination I is constant. However, with n planets, you get n-1 precession frequencies. For example, in 1990, Laskar showed for the solar system, back then including Pluto, that you can compute 8 precession frequencies. These do change a little bit in time, but with all of these put together, you can kind of see that the inclinations of Mercury, Venus, Earth, and Mars are all varying with time now. These are, this is not quite as simple as the picture that I was showing you earlier with just 2 planets and constant mutual inclination. So with n planets, it's easy to calculate these frequencies. So you can do it if somebody gives you all of the parameters that you want to do, that you need in order to it's not so hard to figure out the orbital evolution here. The next thing is to ask what sorts of spin-orbit resonances might you expect for these sorts of multiplanetary systems. The naive thing that you would guess is that, well, this resonant condition, G cosine alpha cosine theta, you can imagine that maybe there's one resonance that can be hit for each of the G, right? Like there's a G1 cosine theta equals alpha. There's a G2, there's a G3. You might imagine that each of these contributes a possible resonance. And you might imagine that each of these contributes a possible resonance. That's probably the simplest guess that you can make for what happens when you increase the number of planets. Even if this is just the guess that you make, there end up being 2 competing effects for whether you would expect planets to be captured into, to be in high obliquity states. The first effect is that as you add more resonances, this means that the planet's spin is feeling a lot more different frequencies. These frequencies kind of compete with one another, and it turns out that that can easily lead to chaotic evolution. This is an old result by Chirikov in 1979. And because you get chaos, you add some tidal dissipation to it, it's pretty easy for the planet to be driven towards, to be kicked out of the high obliquity states by all of that jiggling, and leave the resonances and end up locked down to low obliquity. However, the other competing effect is just that I have a lot of resonances, I hit one, surely I get trapped into one or another, right? So there's also the idea that with more resonances, you may get more chances for capture, and so you get more high obliquity states. So at this sort of level where I've just given you this slide, I don't think that it's very obvious to which of these 2 effects is going to dominate, and whether you should expect more or fewer high obliquity planets in a multiplanetary system. And the story turns out to be that it's kind of complicated. So there were these 2 competing effects. It turns out that there's one extra interesting thing that needs to be mentioned, which is that with more resonances, you actually can get high order resonances as well, where instead of just having one of the G's off to the side, you can have some integer combinations of the G's. So here, for example, this is G1, like 1/2, so this is the average of the two. You can also get like G1 plus 2G2 over 3. You can get various higher order combinations. So there's actually a lot of resonances that pop up here. And the story kind of, for what that has to do, if all I care about are the final obliquities, the story for for the effect of all of those is kind of complicated. Over here, maybe we can mostly focus on the bottom panel here. This is the probability of reaching a high obliquity state. The total probability is the black line here. You can see that for some regions of parameter space, the probability. So this is kind of the very leftmost case corresponds to the two-planet case. The third planet doesn't do anything. Oh, sorry, I'm in a three-planet system. I should have mentioned that. In a three-planet system, this corresponds to the two-planet case. You see that as I increase the effect of the third planet a little bit, suddenly the probability goes to 0. And that's because this chaotic evolution kind of starts to dominate. And then as I continue to increase the effect of the third planet in some way, the total rate probability of being captured into a high obliquity state, this black line, actually becomes slightly higher than the two-planet case. And that's because you have the standard Cassini state for the dominant planet, and you have a bunch of extra resonances that come up. This is the effect of the extra resonances that you get due to the third planet. That's kind of this channel over here. So this red channel here is the chaotic condition where I have much less capture. And this green arrow down there is denoting the regime where I get more captures. And so the story's kind of messy. If you want to actually figure out what's going on, I think that the best thing to do is just to go in and run some numerical simulations for your system of choice at that point. But we kind of understand the mechanisms behind both of these two regimes. Okay. Let's see. Great. The second thing is that I've kind of swept something under the rug as we've been talking so far. It is that yeah, okay, great. So what we've kind of found is that exoplanets that are maybe like less than twice the radius of the Earth are probably actually rocky. If you look over here, sorry, this is work done with former Princeton undergraduate Henry, who is headed to the University of Washington to do some geosciences work right now, actually. Yeah. The picture is that planets that are something like less than twice the radius of the Earth probably have densities that are, so first of all, their densities are broadly consistent with being Earth-like. That's right here, the green dot. The densities are consistent with being Earth-like. So you probably imagine that they're basically rocks. They're big space rocks, right? And something that I kind of mentioned earlier was that as my planets that I've been studying so far, as they spin up, they become more rotationally fat. But if I pick up a rock, right, and I throw it up, it does not rotationally flatten the way that I was showing you guys for this schematic over here. It's kind of tricky because rocks can even tumble, right? Unlike with a fluid, if I throw like a water droplet up in the air, it doesn't do any weird tumbling motions. But if you throw a rock up in the air, it tumbles. It can spin in any sort of axis. It can spin along any sorts of directions. And hopefully maybe this reminds some of you of probably the chapter of your undergrad mechanics class that you forgot, myself included, about the Euler equations. And maybe you guys had this demonstration as well where like they spun the Euler disk and it like took like a minute or something to spin down and it chirps really, really loudly and high pitched. I don't know, this was a formative experience for me apparently. So you can study the tumbling of these space rocks using the Euler equations, or you can use grit as Gunjie developed a couple of years ago with one of her graduate students here. So that's one extra complication, right? That's another complication that you have to worry about. These rocky planets do not behave like their fluid counterparts. And the last kind of thing that turns out to be a little bothersome is that rocky planets actually have tidal models tidal dissipation models that are kind of difficult to understand. They're not very intuitive. A couple of names here in case maybe some of you guys have read or heard about the Maxwell model or the Andrade model. But it is not like kind of the standard, like I just take my oceans and I puff them up a little bit and they dissipate very simply. There's actually quite a bit of work that has gone into doing this, including some stuff from laboratory experiments. to figure out how exactly a rocky body should dissipate energy. So, there are kind of three changes compared to the story that I mentioned earlier. The shape of the planet changes. It's no longer set by its rotation, but you just prescribe the shape and it kind of stays fixed in time. The rocks can tumble, the tidal model changes. You kind of have to cook a little bit. But the summary of what you get out of all of this is that there is a 2-to-1 spin orbit resonance that is in these two planets, and again, this kind of two planet setup. A 2-to-1 spin orbit resonance is actually quite easy to reach. Whether that is because of the tumbling or whether that's because your tidal model kind of prescribes it. And it seems like there's some work that suggests that you might get trapped into this 2-to-1 spin orbit resonance in a tidally stable way, even without a companion, it turns out, which is something that's really, really surprising. And it's something that I think that I'm still working on understanding a little bit. But so yeah, the upshot is that it's a 2-to-1 spin orbit resonance. The planet is spinning twice as fast as it's orbiting, not tidally locked. I guess that's what I'm really trying to say here. There's a lot of complications that come in and interesting stuff to study. But it's also another way that you don't get tidally locked. And it seems like there might be actually as much as maybe it's like maybe 30 to 50%. Earlier I gave you this 25% number, right? This is slightly more efficient at giving you non-tidally locked planets. Okay, so I've fleshed out kind of the outline. Let's just recap. The secular spin orbit resonances that I've told you about can easily force your obliquity to large values. The spin tends to be driven towards subsynchronous for these fluid planets that I was talking about. There are multiple ways of getting captured into these high obliquity states. And between all of them, it's probably likely that quite a few exoplanetary systems are in these high obliquity states. Among the complications, I think the one that I want to highlight is that if your planet is actually quite rocky, again, you get trapped into a supersynchronous instead of a subsynchronous state. So that's kind of a concrete prediction difference between your fluid planets, your larger fluid planets, maybe like Jupiter, Saturn, Uranus, Neptune, or something that's a little bit more Earth-like. Yeah, and I mean, after this, what's next, right? I think that the thing that's interesting is that there are a couple of, is that you can kind of translate this spin evolution into concrete observational predictions or forecasts. You can start building climate models for this sort of stuff, right? There are a couple of built-in climate packages, including some, for example, there's this recent paper by Howard Chen and Hong Jie as well from a year ago, showing that the surface temperature of the planet, as well as the ice, can evolve due to the variation of the spin state of the planet in this TRAPPIST-1 system. So there are a couple of different tools that can be used to do this. I haven't actually done it yet personally. I was kind of, my trip here was kind of to hopefully look into this a little bit more. You guys, some of you probably know better than me what you could do with this information. I do have a list of targets. I think that there are 15 that I'm quite confident in that I have worked out personally. And then there are also about 100 multiplanetary systems worked out by this Natalia Guerrero and Sarah Ballard that came out earlier this year. I think that there are a couple more simplifying assumptions that have been made in this, so this list of targets is a little bit less concrete. But a couple of these 15, I think that they're possibly JWST observable. So if somebody is interested in trying to understand what happens to that, I'd love to chat. Broadly interested in just asking what would be the interesting questions to pose to these systems. What sorts of tooling would be interesting for you, given that some of this stuff probably feels like dark magic. It feels like that to me some days. What sorts of tools would be helpful? Yeah, I kind of wanted to open the floor to that. Maybe we can talk over lunch. Okay, great. Yeah, that's I've already talked. Here's my summary slide. I want to leave up. I already talked about all this stuff, but I will be. I do have a visitor's office up in this building, right? Wait, is it right here? No, JK, that's not my office. I think I have an office somewhere. That's right here. I don't think I'm here for the day. I probably copied that wrong. But you can also shoot me an email or check on my website or anything. I'm always more than happy to talk about this or just various other dynamics problems. I've done quite a bit of work about formation of the binary black holes that we've been observing gravitational waves from, and just various things. I'd be more than happy to chat either today or any time that you guys find convenient. Yeah, and that'll be all.